Okay, we're looking at examples of the singular value decomposition, and I want to look now at an application to solving a system of equations. So we're looking at this system of equations, and if you'll notice, there's something interesting about that system of equations. And that is, there is a solution, and it's x1 equals 1 and x2 equals 2. Try it out. 3 times 1 plus 2 times 2 is 7. 8 minus 6 is 2. 2 plus 4 is 6. 5 minus 4 is 1. And 3 plus 6 is 9. But suppose you didn't know the answer. You couldn't just look at the system of equations and say there is an answer, amazingly enough. It would turn out that you could find the solution if there is a solution to this overdetermined system of equations, many more equations than there are variables. There may be a solution, and it's going to be a solution to this, and it's going to come from the pseudo-inverse. That is, there is actually a single unique solution if it turns out that A dagger A is the identity. But A dagger will not be the identity. In other words, what's happening here is A dagger A is going to be the smaller dimension. In this case, it's going to be a 2 by 2, and it's going to be the identity matrix. And that's going to give us the exact solution when we get to the 2 by 2 system, because the A dagger A will be the identity. But A dagger is going to be a 7 by 7 matrix, and there's just no way in the world that it could be invertible. So here A is only going to be what we call left invertible. Alright, so let's take a look. Let's just do one. Let's just look at this system. So there's my A. That's just the coefficient matrix up here. I'm going to use the P inverse. And notice that's P inverse is the A dagger, and A dagger A here is the identity matrix. Now, of course, if we went in the other direction, A times P inverse of A, then that certainly is not an identity matrix. I think everybody will agree that's not an identity matrix. Okay, so it's an identity in one direction but not in the other. But that means that if I was to actually apply the P inverse to the B, which is the 72619, then lo and behold I get x1 equals 1 and x2 is equal to 2. So what we have here is that A dagger AX equals A dagger B. That's what we just calculated up there. And that means that X is equal to A dagger B. And the reason for that is that A dagger A is the identity. Now let's see what happens. What if one of these numbers was a little different? You know, maybe instead of a 9 here, what if we had, say, an 8? So let's suppose we put the 8 in here. Okay, and if we do the same thing again, then now we don't get the 1 and 2, but notice we still are sort of in the same sort of area there. As a matter of fact, let's not make it so severe. Let's make it, say, like a 8.9. And you can see very close to that 1 and that 2. The same thing, if we change one of these numbers slightly, suppose we make that a 2.1. Okay, then the P inverse A times A is still the identity, and if we execute there, we're not exactly 1 and 2. Even if we change that back to the 9 there, we're still not exactly 1 and 2. So what we have is this may not have a solution at all, because any tiny change to any of these numbers means what? No solution, period. Not one solution, 0 solutions. So what is this 0.9942 Well, what that actually is, if there is no solution, then x equals a dagger b is not the answer, but rather the vector that produces the smallest possible value for ax minus b. Notice if there is an answer here, then ax minus b is equal to 0. So it is possible to have an answer, as we saw back when this was the 9, and up here we had that was equal to the 2. We get exactly this answer, 1 and 2. But even if there is no solution to this problem, we can still get something close.